Previously on intermolecular forces, we were talking about this scenario. We've already discussed London dispersion forces and dipole-dipole interactions. And here we had two molecules, similar molar masses, similar dipole moments, but crazy different boiling points. WTF? What's the force? Well, that force happens to be hydrogen bonding. As you see here, there's an attractive force between a hydrogen atom that is covalently bonded to nitrogen, oxygen, or fluorine. That's super important. The hydrogen has to be bonded to nitrogen, oxygen, or fluorine. Once that happens, it becomes very partially positive. You can see that down in our diagrams here. These hydrogens that are attached to oxygen are partially positive. And then because of that, they are very attracted to partially negative parts of another molecule that's nearby, or a lone pair. Okay, so here, our classic example, we see the hydrogen bond of water. Okay, here's the hydrogen bond between the hydrogen that is partially positive and then that oxygen that is partially negative. And the oxygen is partially negative because of the dipole that's set up, but also, if you know, with water, it has two lone pairs on it. Here's another example over here. We have a hydrogen bond between nitrogen, the lone pair on nitrogen, and hydrogen in neighboring ammonia molecules. Now this little intermolecular force is super strong. It's the strongest of all of our intermolecular forces. So when compounds, molecular compounds in particular, have hydrogen bonding, you're going to see some extreme cases as far as properties are concerned, mainly boiling point that we'll see here in a second. But going back here to this scenario, all right, if we look at the structures of these, because the boiling points were so incredibly different. Why? Well, CH3F, yes, there's hydrogens, yes, there's a fluorine, but the hydrogens are attached to carbon. And so we know that a carbon-hydrogen bond is traditionally nonpolar. So yes, we have the dipole moment and we have dipole-dipole interactions. But this molecule over here, the hydrogen is going to be attached to that oxygen. And because of that, right here, this hydrogen is eligible for the hydrogen bonding. And that's why we see such an incredible difference between the boiling points. And here we see a nice little chart kind of referencing this. If you look at hydrogen bonding to different atoms, let's see, down here looking at the carbon group, group 14, we've got CH4, then SiH4, GeH4, SnH4. As the molecular weights are going up, so is the boiling point temperature. And that is what we expect because, as we previously discussed, the London dispersion forces are increasing with the molecular weight, so we see an increase with the boiling points. Same thing we see here with HCl, HBr, HI, or H2S, H2SE, H2TE. These are the trends seen with hydrogen compounds in these groups. What I have covered up, though, is, ta-da, the effect of hydrogen bonding. Water forms hydrogen bonds and has a crazy boiling point of 100 degrees Celsius. Then, when hydrogen bonds with sulfur, there's a sudden drop in that boiling point temperature because we no longer can form hydrogen bonds. Same thing, hydrogen fluoride can form hydrogen bonds, hydrogen chloride cannot, ammonia can, pH3 cannot. So you can see the dramatic effect that hydrogen bonds have on the boiling points because, again, when we boil, when we vaporize, we need to break the intermolecular forces. So all down here in this part of the graph, we're simply breaking London dispersion forces, maybe some weak dipoles. But water, HF, and NH3, we're breaking the hydrogen bonds. Much more energy is needed. Hydrogen bonding is super critical to you, your DNA. I'm sure you have mentioned that hydrogen bonds hold our DNA strands together. We've got the phosphate deoxyribose backbone, but then holding the strands together, creating the double helix that we know, are these hydrogen bonds between the base pairs. All right, so that's super important there. So the last thing here, if you're given a compound, either on paper or perhaps with a structure, you should be able to figure out what type of intermolecular forces are going to be expected. All right, so here we have three substances. And first off, we remember that our London dispersion forces are present in everything, even monoatomic elements. Okay, so all of these compounds will experience London forces. Dipole-dipole, well, we need to have polar bonds. CH4, of course, has all CH bonds, which are all nonpolar, so no dipole-dipole for CH4. CHCl3, okay, yes, each of the carbon-chlorine bonds are polar, and this is a tetrahedral formation, if you remember. So with an odd number of dipoles, they won't cancel out. So this molecule will indeed experience dipole-dipole interactions. Down here, CH3, CH2, CH2OH, that's propanol. Okay, the carbons, that's where the H's are. And then this carbon's attached to this carbon, which has two H's off of it, which is attached to this carbon, which has two H's off of it, which is attached to this oxygen, which is attached to this hydrogen. So we do have a carbon-oxygen polar bond and a hydrogen-oxygen polar bond. This part of the molecule will actually be bent because of the two lone pairs on oxygen. So those dipoles will not cancel out. In fact, they're pointing towards the oxygen. So yes, this will also experience dipole-dipole interactions. And then lastly, hydrogen bonds. The hydrogen must be attached to nitrogen, oxygen, or fluorine. So these hydrogens are not, this hydrogen is not, but this hydrogen is. Okay? And so because of that, our last molecule, propanol, will also experience hydrogen bonds. A little messy on this page, but hopefully you figured that or followed me. CH4, CHCl3, and the propanol all will have London forces. All of them do. Dipole-dipole, you need to have a polar bond or a polar molecule. And so yes, the last two have that. And then hydrogen bond, again, you must have the hydrogen attached to nitrogen, oxygen, or fluorine in order for hydrogen bonding to be possible. Welcome to the wonderful world of hydrogen bonding and intermolecular forces. I hope this helped. See you soon.